Welcome to the second session on the series of lectures, Applications of Nested Interval Theorem. Today, as a second application, we are going to prove the intermediate value theorem for continuous functions. So we will start with the definition of continuity, but before that, so the reference will be my book on basic course in real analysis. Also, there is an article of mine, nested interval theorem and its application, which gives about 7 or 8 applications, but this series we will deal with only 3 applications. This article may be downloaded from this site. So let us start with a recollection of what is why thing. Okay, so for me, J is an interval R. This interval may be finite, closed, open, or semi-open, semi-closed, or it should be infinite interval, or it should be R itself. Okay, right? Okay, and fix a point A in J. Then I say F from J to R is, did I share it? Yeah. So J is a subset of R. It's an interval of any one of this form. Fix an A in J. I want to say F in J, F from J to R is continuous at A if, let us look at a picture. Okay, this is my J and this is my codomain R, and F is from here to here. Okay, suppose I have a point A here, okay, and I have a point F of A here. Okay, I am given an epsilon. I can form the interval F of A minus epsilon to F of A plus epsilon, right? Then what is that I want to say? Continuity means there is a delta such that look at A minus delta to A plus delta, right, and intersect it with J. Then for all x here, Fx should lie here. Okay, so let us write it carefully. If for every epsilon positive, there is a delta positive, so that, okay, for every x where it should be an element of this, and in the interval A minus delta A plus delta. Notice that why I am writing, suppose my J is this, okay, A may be the left hand point. In that case, A minus delta to A plus delta, that will be only this, intersect with J. Or suppose it is an end point, right hand point, then call it A, then A minus delta to A plus delta, therefore that will be intersect with J, will be only this point. Okay, so for all x in this, what do I have? We want to claim Fx belong to F of A minus epsilon to F of A plus epsilon. This is the continuity definition, right? In terms of inequality, how will you write? For every epsilon positive, there is a delta positive, so that, okay, x belong to J and mod x minus A less than delta implies mod Fx minus Fa is less than epsilon. Okay, please pause just to recall if this is the you are learning analysis just now. Okay, it is always worth going through the definition once over, and remember the first definition I wrote somewhat geometric, that will be very useful, though we should also be very comfortable with inequality, right? The key observation is the following. Suppose F from J to R is continuous at A, and suppose F of A is non-zero, then either F of A is positive or F of A is negative, right? Then what I want to say is then the sign of f, okay, persists, okay, remains the same. That means remains the same in an interval, of course, intersect with j around a. Okay, this is the I just said it intuitively, but let me explain that in detail. So suppose f of a is positive, right? Let's look at the picture. Maybe this is my 0, this may be my f of a. F of a may be very close to 0, but still it's positive. I'm just magnifying so that it looks as though it's far away from 0, right? Then what I can do is, as an epsilon, I can take f of a by 2. Then this will be f of, okay, f of a minus epsilon. This is f of a by 2, right? And this will be 3fa by 2. This is same as f of a plus epsilon, right? Then what do I know? Then I know there is a delta positive, so that if x belongs to j and, okay, mod x minus a is less than delta, that is x belongs to a minus delta to a plus delta intersect with j, then fx should lie in this interval, f of a by 2, 3f of a by 2, right? Now remember, f of a is positive, therefore that means, okay, for all x in this interval, okay, fx is positive. Do you follow that? So similarly, if you say fa is negative, let us say this, I can take fa and take minus fa by 2, then fa plus epsilon will be fa by 2, and this will be 3fa by 2, and you carry out the same analysis. So what have we shown? Just, okay, let us summarize. Thus we have shown that is there exists a delta, so that for all x in j intersect with a minus delta to a plus delta, right? That is fx is positive, assuming fa is positive. And similarly negative. So that's what we meant by saying in a neighborhood, this is an interval around a, okay, as I said, it may be of the form this, or it may be of the form a plus delta, or it may be of the form a minus delta to a, if it happens to one of the endpoints. So in these intervals, the sign of f remains the same, namely the sign of fa. Okay, pause, review, proceed. So this is known as local property, right? Yeah. For example, if I have a continuous function f of x equal to x on the interval minus 1 to plus 1, okay, at x equal to half, fx is positive, but I can't expect it remains the same, right? This is 0, this is half, so in an interval it will remain, but I can't expect it retains the same sign throughout the interval. I am not saying that. Do you follow that? So it's only local. But suppose I want to say, right, suppose I want to say f retains the same sign on all of j, that is f is from j to r, this is continuous on j. What does it mean? That is continuous at each and every a in j, right? Okay, then I want to say f retains the same sign and assume f of x is different from 0. Then, okay, sign of f on j is the same, is a constant. That is always positive or it's always negative. This is a global property. Okay, if you are a BSc student, you may be intimidated by these things, but just to learn this kind of thing. If you want to forge ahead in advanced mathematics, this way of thinking will be useful. Okay, this is what intermediate value theorem wants to say. That is, what does intermediate value theorem wants to say? It wants to say if I have a continuous function from an interval to R, and if the continuous function does not vanish anywhere on the interval, then it will retain the same sign all through the interval. Do you understand? Okay, right? Pause, review, read. If necessary, you rewind, go back, and let me repeat what I said. F is continuous on interval j, and f is not 0 at anywhere on the interval, then f retains the same sign on the entire interval. Either f is always positive on j or f is always negative on j. Here you see that in this case f vanished at one point. That is why it would not give the same sign. Yeah? Do you like it? Okay. So, this makes me wonder. See, I'm trying to think, but trying to arrive at a theorem logically. So, right. So, if I suppose f is a continuous function from j to r, right? Continuous on j, and suppose f does not keep the same sign. Same sign on j. What does it mean? That means there exists a in j and b in j, so that the sign of fa and sign of fb, okay, one is positive, one is negative, right? Maybe fa is positive, fb is negative, or fa is negative and fb is positive, right? If it does not keep the same sign, this is what it means, right? So what I should like to say, then I would like to say, then there exists a c in the interval j, so that f of c must be 0. F of c must be 0. Think logically. See, this kind of logical thinking is what is missing. You should learn from my foundation course. Okay, what did I say? If for all x fx is non-zero, then it retains a same sign. So if you say if it does not retain the same sign, then what does it mean? Logically, there should exist some x so that fx is 0. Do you understand this? For all x in j, fx is not 0. Then sign of f is constant. So if sign of f is not constant, that means there exists an x in j so that fx equal to 0. Do you understand this result? Yeah. So we are actually going to prove something stronger. So let us prove. Okay. Intermediate value theorem. Let f from a b to r be continuous. Assume that, okay, fa times fb is negative. Then there exists a c in between a and b. Okay, so that f of c is 0. What does it mean? This means fa and fa have opposite sign. fb have opposite sign. One is positive, one is negative. Okay, and notice that c cannot be a, c and c cannot be b. Right? If one of them is c is one of the endpoint, then this will be 0. But it is strictly less than 0. Therefore, we can even write there is a c strictly between a and b. Do you understand this? Okay. Now let's go through proof. So proof. So without loss of generality, let us assume fa is negative and fb is positive. So the picture is something like this. This may be my a, This might be my B, and FA may be here, and FB may be this. This is BFB, and this is AFA. Okay. So I want there is at least one point where C is 0. Right? So as I said, therefore I have an interval AB. Okay. Call this as J naught. Okay. Right? So what happens? So here f of A is negative and f of B is positive. Right? So I wanted nested interval theorem. How do you think I will use? I will use the so-called again bisection method as I explained in the last lecture. Okay. So bisect this interval AB. Okay. This may be its midpoint. Okay. C is the midpoint. A plus B by 2. Now let us look at this interval. Okay. Now let us look at this interval. Okay. Now what are the possibilities? F of C may be 0, in which case I am happy. I already proved the result. Right? Suppose f of C is not equal to 0. Then what happens? F of C may be positive. Here f of A is negative and f of B is positive. Suppose f of C, okay, is positive. Then let us look at this interval A to C. Therefore, at one endpoint, namely A, f of A is negative. At the other endpoint, f of C is positive. But the interval is half of the original interval. The size of the interval is half of the original size. Right? Okay. Yeah. Or what may happen? Suppose f of C is negative. Then f of A is negative, f of C is also negative. So what do you think I should do? I should consider the interval C to B, because then f of C will be negative, f of B will be positive. Remember, f of C is 0, there is nothing. Proof is over. Do you follow that? Yeah? Okay. So how will I write? If f of C is 0, then we stop. Then the theorem is proved. Okay? If not, f of C is positive or f of C is negative. If f of C is positive, then consider J1 equal to A to C. Or if f of C is negative, then consider J equal to C to B. Right? J1 equal to C to B. You understood? Yeah? Therefore, what I have done? Okay, we have found an interval J1 such that J1 is contained in J0 and length of J1 is half of length of J0, and if I call the A1 B1, okay, let me call J1 as A1 B1, then f of A1 is negative and f of B1 is positive. Okay, right? So what do you think I will do? Now I think all of you know, right? This is my J1, A1, B1, f of A1 is negative, f of B1 is positive. Then what do you think? I will start with the C1, which is the midpoint of these two fellows. Right? Right. Now, if either if f of C1 is 0, then again stop. Otherwise, if f of C1 is negative, then consider this interval. If f of C1 is positive, then consider this interval. Therefore, I found a J2. Do you understand this? Okay. J2 is A2, B2, which is a subset of J1, so that f of A2 is negative and f of B2 is positive. Right? And what is the length of J2? Is half of length of J1. J1, length of J1, therefore it is 2 to the power minus 2 of length of J0. That is 2 to the power minus 2 of B minus A. Have you understood? So suppose I have produced Jn, which is A n B n, okay, induction step. Okay, so that Jn is contained Jn minus 1, length of Jn is 2 to the power minus n b minus a, and if Jn is A n Bn, then f of An is negative and f of Bn is positive, right? So then I can produce a Jn plus 1. How will I produce a Jn plus 1? Again the same trick. Let n Bn, let Cn be the midpoint. Then if f of Cn is 0, stop. Otherwise, what will I get? Then if this is f of Cn is positive, then this is the interval I will consider. Okay, and if f of Cn is negative, then this is the interval I will consider. That will be my Jn plus 1, right? Therefore Jn plus 1 is again contained in Jn, and call this as An plus 1, Bn plus 1. Length of Jn plus 1 is half of length of Jn, therefore it's 2 minus 2 to the power n plus 1 into b minus a, and f of an plus 1 is positive and negative, and f of bn plus 1 is negative, positive. Okay, so if at nth step the midpoint is such that f vanishes at midpoint, I can stop. Otherwise I have a sequence Jn, this is a nested sequence with what property? Jn plus 1 is contained in Jn for all n, and length of Jn is 2 to the power minus n b minus a, and 3 if f of an is negative and f of bn is positive, where Jn is a and b. Okay, pause, review, proceed. Okay, now we are used nested interval theorem to construct, we are ready to apply nested interval theorem because we have constructed a nested sequence of closed and bounded intervals, right? And notice that length of Jn is minus 2 to the power b minus a, that goes to 0. Therefore intersection of length of Jn, okay, n equal to 1 to infinity, this is some singleton, call it alpha. Alpha is a real number, right? Notice that alpha belong to AB. Why? That means alpha belong to Jn for all n, and each Jn is a subset of AB. Therefore alpha belong to f of AB. Is it clear? Right. Now I want to say f of alpha is 0. Suppose not. Okay. Notice that alpha has to be in the open interval AB. Sorry, let's just, okay, I want to claim f of alpha is 0. Suppose not. Okay, then f of alpha is positive or f of alpha is negative, right? Now since alpha belong to the interval AB, f is continuous at alpha, right? Suppose f of alpha is positive, then what do I know? So this is my AB. Okay, remember my alpha could have been B, maybe. Okay, but I am just assuming alpha is an interior point. If alpha is equal to B also, the argument will work. Okay, so what do I know? There is an interval alpha minus delta to alpha plus delta intersects with the interval AB, so that for all x here fx must be positive because f of alpha is positive. This is the local property. we already observed by local property there exists a delta positive such that for all x in alpha minus delta to alpha plus delta. It may be like this, or it may be like this also, alpha minus delta to alpha, which is b. It may also happen, doesn't matter, right? Okay, now let us look at, so let us look at the length jn. This I know is 2 to the power minus n b minus a. Yeah, right. Now alpha belongs to jn for all n. Yes. So I want to claim that jn, there is an n in natural number, so that for all n greater than or equal to n, jn is actually contained in alpha minus delta to alpha plus delta. Okay, this is again exactly the same way we argued in Bolzano-Weierstrass theorem, but let me go through the proof once again. If you are a beginner, it is always good to review the proof again and again. Why? Because start with any x in Jn, right? Therefore, what is the length of x, the distance between x and alpha, since alpha and, okay, this is my Jn, and alpha and x are some 2 points here. Okay, they may be somewhere, I don't care. Okay, therefore the total length will be less than or equal to the power minus n into b minus a, right? So if I choose an n so that 2 to the power minus n b minus a is less than delta, right? Because 2 to the power minus n b minus a goes to 0. Therefore there is an n so that this happens. Yeah, therefore in particular for all n greater than or equal to n also, okay, 2 to the power minus n b minus a is less than or equal to 2 to the power minus n b minus a, which is less than delta. That means, okay, that means for all x in jn, n's like this, okay, mod x minus alpha is less than delta. That means x belongs to alpha minus delta to alpha plus delta. That implies jn is contained in alpha minus delta to alpha plus delta. Yes, do you follow that? Yeah. In particular, therefore, let's look at a capital N and b capital N. Both belong to Jn, which is contained in alpha minus delta to alpha plus delta, right? Therefore, f of an must be positive, because for all x in alpha minus delta to alpha plus delta intersected with j, fx must be positive, right? But an x equal to an, that's an element of jn. Jn is a subset of j, therefore x an belong to this set, right? Therefore f of an is positive, but by our choice f of an is negative. This is a contradiction. Therefore what I conclude? I conclude f of alpha greater than 0 cannot happen. In a similar way, f of alpha negative cannot happen. But f of alpha is a real number, right? So I can apply law of trichotomy. That means f of alpha is either 0 or positive or negative, and exactly one of them happens. But we know this cannot happen and this cannot happen. Therefore f of alpha is 0. Yeah. Pause, review, proceed. So many of you have learned intermediate value theorem in the following fashion. Let me recall the standard version. F is continuous from A, B to R. Okay, and assume that, okay, there is a real number lambda which is such that f of b. Then there is a c between a and b such that f of c equal to lambda. That is the intermediate. Lambda is a value in between two values, f of a and f of b. Then that lambda is also a value of the function. That means there exists lambda is a value taken by the function at the point c. There may be more than one c, but we are getting at least one c. Okay, this can be reduced to the earlier case because you look at g of x equal to, I want negative, therefore let me say f of x minus lambda. Therefore f of a, since f of a is less than lambda, g of a is negative and g of b is f of b minus lambda, therefore it's positive. Therefore there is a c so that g of c is 0. That means f of c is lambda. Right? So this is a standard version. Now let's look at, I said if you have from an interval, this is any interval, any, okay, as I said, AB, 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 minus infinity to A, B to infinity, R, any one of the interval, okay, continuous, assume fx is different from 0 for all x in G. Then f has the same sign. Yeah, this is what we want to prove. Okay, so this is the global version we said, global property. But remember, we want the domain to be an interval. We use the fact it's an interval. Yeah, okay. Now why should it say this? Suppose not. Okay, that means what? Okay, fix an A is it. Okay, there exists A and B in J such that f of A is positive and f of A is negative and f of B is positive. See, now this may be the case A, B, or it may be A, B. I don't know which way. Do you understand that? Yeah. Now restrict f to this function. Okay. Either A, B if A is less than B, or restrict f to B A if B is less than A. Right? Then what happens? Now in this case you can see f A is negative, f B is positive. Therefore by intermediate value theorem just now in our version there exists a C in the open interval AB such that f of C is 0. But AB is contained in J and C belongs in the open interval AB. Therefore C belongs to J. That means f of C is 0. That's a contradiction because fx is not equal to 0. Did you understand the proof? If you didn't, I will look at the second case. Suppose this is my BA. Okay, so f of A is negative and f of B is positive, right? So what do I know? There exists C such that B less than C less than A such that f of C is 0 by my version of intermediate value theorem. Now remember the interval AB, A and B are in the interval, right? In J, right? C is there, therefore C is a point of J, right? Then only I can talk about f of C. That also you should remember, right? Okay, but why this is a contradiction? Because we said for all x in J, fx is not equal to 0. Okay, but then we are getting f of c is 0. Yeah, okay, so this is how we proved all the thing. I hope you enjoyed. If you are a beginner, okay, please go through it once more. You will appreciate. If you had already learned real analysis, even then I am sure there will be one or two things, okay, and a perspective which you have not seen earlier. Okay, that is the way you can improve. I hope all of you enjoyed. We will meet with the in the next session. That will be the last session of the series on applications of nest and row theorems. Okay, take care, stay safe. We'll meet again.